Welcome to Lecture 7. Today's topic focuses on two key technologies that play a crucial role in securing digital payments: tokenization and encryption. Both are vital for protecting sensitive payment data from cyber attacks, fraud, and theft, ensuring that businesses and consumers can engage in transactions safely. By the end of this lecture, you will understand what tokenization is and how it works in the context of payment security. Learn about encryption and how it protects payment data during transactions. Explore the differences and use cases of tokenization and encryption. Identify how these technologies contribute to regulatory compliance and risk management. The importance of payment security. In today's digital economy, payment security is paramount as businesses and consumers increasingly rely on electronic payment methods. As transactions move through digital payment systems, there are numerous opportunities for sensitive information, such as credit card numbers and personal data, to be intercepted and misused. Therefore, it's critical to employ advanced security measures to protect this information. Two of the most effective security technologies used in payments are tokenization and encryption. They ensure that sensitive payment data is either replaced or masked, making it difficult for hackers to access or use the data even if a breach occurs. What is tokenization? Tokenization is a security process where sensitive data, such as a credit card number or bank account information, is replaced by a non-sensitive randomly generated value called a token. This token has no intrinsic value or meaning outside the tokenization system, so even if a hacker gains access to the token, they cannot use it to extract the original sensitive data. How tokenization works? Payment initiation. When a customer initiates a transaction, their payment information, for example, card number, is captured by the payment system. Token generation. Instead of storing or transmitting the actual payment data, the system generates a unique token to represent the payment information. Transaction processing. The token is sent through the payment network to complete the transaction. Mapping. On the receiving end, typically the payment processor or acquiring bank, the token is mapped back to the original payment information for transaction completion. Storage. The sensitive data is stored securely in a separate, highly controlled environment known as a token vault, while the token is used for transaction processing and data storage. Key characteristics of tokenization. Uniqueness. Each token is unique and random with no mathematical or logical relationship to the original data. Non-reversible. Tokens cannot be converted back into the original sensitive data without access to the secure token vault. Scope. Tokenization is used primarily for protecting card-on-file payments and recurring transactions. Reduced risk. By replacing sensitive data with tokens, businesses reduce their risk of exposure in the event of a data breach. Example of tokenization. Imagine you're shopping online and enter your credit card details. For example, 4,111.11.11.11.11.11. Instead of transmitting your real card number, the e-commerce site's payment gateway replaces it with a token like AF 3291.87 BDF 193 ED1C, which is then used for the transaction. Even if a hacker intercepts this token, they won't be able to extract your card details from it. What is encryption? Encryption is the process of converting sensitive data into an unreadable format, ciphertext, using an algorithm and an encryption key. Only authorized parties with the correct decryption key can convert the encrypted data back into its original format, plain text. How encryption works. Data encryption. When a customer provides their payment information, for example, credit card number, it is encrypted using a specific algorithm and encryption key. Secure transmission. The encrypted data is transmitted through the payment network, ensuring that even if it's intercepted, it remains unreadable. Decryption. At the receiving end, for example, acquiring bank or payment processor, the encrypted data is decrypted using the corresponding decryption key to complete the transaction. Data protection. Encrypted data can only be accessed by authorized parties with the decryption key. Key characteristics of encryption. Mathematical relationship. Encryption uses mathematical algorithms to scramble data, creating a reversible relationship between the ciphertext and the original data. Decryption key. A key is required to convert the ciphertext back into readable plaintext. Used in transit. Encryption is commonly used to protect data while it's being transmitted across payment networks or the internet. Protecting data at rest. Encryption is also used to secure stored data, such as payment details saved in databases or cloud environments. Example of encryption. Let's say you're making an online payment and your credit card number is 4111 1111 11 11 11 11. Encryption would convert that card number into something like a 3F7C9 BD183764F using an encryption algorithm. Only the authorized payment processor can decrypt it to access your actual card number for completing the transaction. Use cases for tokenization and encryption. Both tokenization and encryption are widely used in the payments industry to safeguard data. Here are some specific examples of their applications. Tokenization. Card on file. Tokenization is frequently used by businesses that store customer card information for future or recurring transactions, such as subscription services, Netflix, Spotify, or e-commerce platforms. Mobile payments. Tokenization is used in Apple Pay and Google Pay, where a tokenized version of the card is used for contactless payments instead of transmitting the actual card number. Encryption. Data in transit. When a customer enters their payment information online, it is encrypted as it travels between the merchant's website and the payment processor. Data at rest. Encryption is used to secure stored payment data in databases or cloud environments, ensuring that sensitive information is protected from unauthorized access. How tokenization and encryption contribute to compliance. Both tokenization and encryption help businesses meet industry regulations and standards designed to protect sensitive payment data. Here are some of the key compliance standards impacted by these technologies. PCI DSS, Payment Card Industry Data Security Standard. Tokenization and encryption both contribute to PCI DSS compliance, which requires businesses that handle card payments to protect cardholder data. By using tokenization, businesses can reduce the scope of PCI DSS compliance since tokens are not considered sensitive cardholder data. GDPR, General Data Protection Regulation. In the European Union, GDPR mandates strict data protection measures, including encryption, to safeguard personal data, such as payment information. Failure to implement adequate security measures can result in significant fines and penalties. PSD2, Payment Services Directive 2. In the EU, PSD2 requires strong customer authentication (SCA) and secure transmission of payment data, for which encryption plays a key role. The role of tokenization and encryption in risk management. Tokenization and encryption are both critical tools in managing the risks associated with handling sensitive payment data. Here's how they contribute to risk reduction. Minimizing data breach. Impact. If a data breach occurs, tokenization ensures that the stolen data, tokens, is useless to attackers since it cannot be reversed into the original card data. Similarly, encrypted data is unreadable without the decryption key, rendering it useless to hackers. Preventing fraud. Tokenization helps reduce fraud in card-not-present (CNP) transactions, as tokenized payment data cannot be reused outside of its original transaction context. Encryption, meanwhile, secures the data as it moves through networks, ensuring that payment details are not intercepted or altered. Protecting brand reputation. By implementing tokenization and encryption, businesses can demonstrate a commitment to security, helping protect their brand reputation and build trust with customers. The future of payment security. As payment technologies continue to evolve, so do security threats. Tokenization and encryption will remain foundational technologies in protecting payment data, but new innovations may enhance security even further. Blockchain technology. Blockchain offers a decentralized and tamper-resistant way of processing transactions, potentially reducing the need for traditional encryption and tokenization methods. Advanced authentication. Tokenization is likely to evolve alongside biometric authentication methods, for example, fingerprints, facial recognition, to create even more secure payment experiences. AI and machine learning. AI-driven security systems can detect unusual payment patterns or fraud attempts in real time, adding an extra layer of protection alongside tokenization and encryption. Key takeaways. Tokenization replaces sensitive payment data with a non-sensitive token, minimizing the risk of exposure during storage and transaction processing. Encryption scrambles sensitive data into ciphertext, ensuring its protection during transmission or while at rest. Both technologies contribute to compliance with regulations like PCI DSS, GDPR, and PSD2, helping businesses protect sensitive customer data. Understanding the difference between tokenization and encryption is essential for businesses to implement the right security measures based on their specific payment environments. That concludes Lecture 7 on tokenization and encryption in payment security. Feel free to ask any questions, and I'll see you in the next session.